So today we are going to discuss about recurrent neural networks, and this is outline of my presentation. Like we will discuss what are recurrent neural networks, what we mean by them, and what problems we face, like vanishing reading problem, exploding reading problem, and how to solve that problem. And then we will briefly discuss about long short-term memory networks. That is a type of RN only. And then we will see how to implement these networks using Python. That is the total outline of my presentation is. And first we see what we mean by these networks. So a brief about neural networks in general. Like we have different types of networks with us, and you must have seen till now. Like if you have to solve some problem with table data, you have a table data with you, some data in table form, rows and columns in features in columns and rows of data samples. Then and that problem, if you want to solve for regression, like predicting some number or predicting some class, then it's a classification problem. Then we use artificial neural networks for that purpose. And if some image video is there, then we go for convolutional neural networks. And today that we are discussing these recurrent neural networks, we use these networks for time series data. Wherever there is some time series, like some sequence is there, some time sequence is there, like text, even text is sequence. If I'm writing some text, like I live in Chandigarh. So I live in Chandigarh is a time sequence. So I is coming first, then live is following I, so on. Or some speech, or some anything like a stock price of a stock. We'll see this example only today. So stock price is also time series data. So wherever there is some time series, then we will go for recurrent neural networks. And some other types you may have seen is unsupervised learning, self-organizing maps, Gaussian machines, and autoencoders. So our focus today is on recurrent neural networks. So this is our human brain, from where we have got this institution of this neural networks. So our brain normally has three parts broadly: cerebellum, and brainstem. And the main part of this is first thing, cerebrum. And so cerebrum mainly contains four parts. One part is temporal lobe. That acts as ANN for us. We have inspired our ANN network from this part of the brain. That is used for this, making some predictions and classification on numbers data. Then we have this.
मणि जी इधर से कर दो.
Then we have this
इतने में कर दो.
occipital lobe that
काफी गंदा है.
That works as a.
हाँ तो साइड पे कर दो.
अमित सर आपका माइक ऑन है सर. अमित सर. Then we have this occipital lobe that acts as a computer vision for us, human vision, that is responsible for human vision. Then this frontal lobe is all that we try to do things in time series, in sequence things. They come here. And how this RNN is related to artificial neural network, the fully connected networks that you have seen earlier. The normal structure of a ANN looks like this, that we have some input layer. We'll suppose we have got three inputs. And we have got some neurons in hidden layer, like here 4 neurons in the hidden layer. And you have got two outputs. So this is a normal network that we use in fully connected networks, or we call them artificial neural networks. And how RNN is different to this ANN? This we will see. Somebody has raised their hand also. Any issue? I hope it is fine. You can ask me questions in between. There is no issue. I'm just considering that you already have some background in this deep learning, and you know ANN part, CNN part, very well. Am I right, or is it fine that you know this deep learning part already? Yes, please. Anyone? Are you comfortable with ANN and CNN part? So then in that way, I will take my discussions forward. Yes, please. Amit sir,
Sir, please go ahead.
uh, sir, they know ANN part well, na? The introduction part they have done already.
Yeah, yes, they have covered the basics of neural network CNN algorithm, deep learning.
Thank you. So this is a common structure of a ANN part, and it has got these normal, at least it will have three layers: input layer, hidden layer, and output layer. So now how RNN is different from this ANN part? So what we are going to do, we are going to squeeze this network. So now the different weights, all inputs in this, you can see that all inputs have got different weights. This is different weight, this is different connection and different weight. So if it is a one neuron, it is a two neuron, you can think it's a W21. This is W2, W21, W11, it is W21, like that. So all weights are different. They have different values. But here what will happen? All inputs will share the weights. So there is a concept of weight sharing. That is the first difference. All inputs and hidden layers, they will share the weights. So learning will be shared. Learning is going to happen in weights only, and that learning will be a common learning, shared learning. The concept of shared learning is there. So if I'm inputting some text like I live in Chandigarh, so wherever this text comes, like live, either before sentence or in the end of sentence or anywhere in the text it comes, it will be learned as it. So it is basically spatial invariant. Learning is spatial invariant. Whereas in ANN part, all inputs we learn in them at a particular place. If some input is input one, we are learning it as an input one only. If it comes somewhere else, then we have to learn it again. But in this RN part, we have this shared learning, weight sharing is there. So input can come anywhere in the text or in our content of speech. So we are going to learn it anywhere. So that is called spatial invariance. Then another view we can have this. This is the input, and this is our output, and this is our hidden layer. Then all other things, they are interconnected. Just I show you some other figure that will become more clear. Is your hidden layers are behind this hidden layer. It's a time series. They are interconnected. Like this. This is basically suppose I have input I live in Chandigarh. Like that. All text is like there. So this same weight. So this is my input. Suppose this is my input x1, and this is my hidden layer. This is my output layer. Then this weight, if I'm calling as hx, then this weight is shared all across all inputs. The same weight, the same connection, not different connection. And again, same. It is if it is also h, then this weight is suppose hh between two hidden layers. Then this same weight, the same weight being shared all across the network. And same thing here. Suppose I'm taking this weight as YH, this weight between output and hidden layer. Then this weight is same here. It is being shared. So just you can think it's a single connection, but it has got time series, time steps. These are all time steps. in forward direction that we are showing, it is the time steps. But network is same. You can think it's the same network having these three things, but it has been enrolled in time. And time step for us is this one word here for this particular example. So one time step is I, other time step is live, another time step is in, so on. So main thing is that all weights are shared, same weights. You can think this is WHX and this is WYH and this is WHH between hidden layers. And another view of saying this is that time is in this direction, and you will have multiple inputs at a time. That you can think of a batch size. You will have some batch, like your batch of 32. So 30 input sentences can be fed to the network. So these 32 network sentences will be processed in the parallel. So everything has all in hidden layer and on output. Suppose I want to predict the next word. So my first sentence is I live in Chandigarh. Next sentence is something that I teach in CCT. So this is my second sentence. So this will teach like that, and it's predicting for each separate. So it's a batch size. I can have multiple sentences input at the same time. Whenever. This is how basically it is helpful to us, that it allows us to work with sequences of data like text, audio, and video. Anything that is in sequence can be processed using recurrent neurons. Normally we show it like this. And it is unrolled structure that we have just seen. This is without rolling, this is with rolling. So just you can see there are multiple copies of the same thing. You think it's a multiple copies of the same thing. And different examples of these networks, like suppose the problem is that you want to predict the caption of the image. It's the image captioning. So this is image, and you want to predict its caption. So you can have image as a single node, and you're predicting a lot of words for that. So it can be one-to-many problem. Or you're providing some input, one word, you want to predict rest of the sentence. Like I'm providing I have to predict live in Chandigarh. So one input, many outputs. This can be ARNI. Or it can be reverse, many to one. Suppose I want to input some text like thanks for a great party at the weekend. We really enjoyed it. Now we want to predict the sentiment of this text, that it's a positive sentiment or a negative sentiment. So we have one output and multiple inputs. Some other types can be many to many. Like you want to translate this text. I'm a boy who likes to learn. So I have multiple inputs and multiple outputs. Like you want to translate it to Hindi. So I'm a लड़का हूँ जो learning like that. So multiple inputs, multiple outputs. Or you can have some like you want to create subtitles of the movie. So movie is coming in frames, multiple inputs, and subtitles will be different words. So that is a many to many problem. Now the big problem with this RNN is vanishing gradient. Normally our text is quite long. We have a long sequence of text with us, and suppose we want to predict the next word. I'm entering some text here, like I live in Chandigarh, and I want to predict every word, like I want to predict what will come after I, or you want to translate it into Hindi. मैं चंडीगढ़ में रहता हूँ, like that. So it's a long sequence. So it has to, back propagation. You must have done that. We have to back propagate the error. Only then learning can happen in a network. First we do the forward direction, then we feed our error in the backward direction. Now here it's a long sequence of text. What will happen when your network will start going in the backward direction? It has to cover a lot of distance, and during that distance, the gradient. You must be knowing that when you do back propagation, your gradient is the thing that goes back. Gradient is the thing that goes back in the network. Now, if it's a long sequence of text, this gradient can become lesser and lesser, or it may explode. Two things may happen. Like, uh, suppose this was an error here at time t, and you want to backpropagate that error through the network, then this will go like this, in this direction and back in time. Now, when it is going back in time, over a time, if it's very small number, gradient is very small, then it will become it will almost vanish here. If it is very small, if it is less than 1, then this gradient is going to vanish after some time. Or if it is more than 1, like it's a big number, then you are multiplying it again and again, then it may explode. That is called gradient exploding. So one of that thing may happen. Like this. If your weights are very small, they may vanish, or if they are very large, they may explode. Since you are going to multiply them over a long sequence, over a long period. So how to solve this problem? If it is exploding, then what we can do? We can truncate the backpropagation. That we can make some limit that we are not going to backpropagate beyond 10 nodes. Beyond 10 nodes, we are not going to backpropagate our gradient. One thing we can do it, but it will have some issues. Then your memory of the network is limited. You have limited memory over the last 10 time steps. Beyond 10 time steps, your network can't remember anything. Suppose if some you're writing that some girl is there. Suppose Meena is there. Meena is studying in Nitter, and now we have to see whether what we have put here, he or she. He lives in Chandigarh. Now, what he or she will come to decide that network has to learn that it is a girl. Somewhere we are talking about a girl. So if we are restricting its backpropagation up to some nodes only, then this memory is lost. Or another solution for exploding gradient is that you can clip the gradient. You can put some limit that your gradient can't go beyond 1. More than 1, it can't go. Just up to that point only. So that is called gradient clipping. But it will lead to some errors in the network. It will add to some approximation of the gradients. So that will hamper our accuracy or performance of the network. And if it's a vanishing gradient problem, then that can be solved using that. You can have some large weights with you. You can initialize large weights so that when they travel back in time over a lot of networks, a lot of nodes, still they have some good value with them. Or another solution is using long short-term memory, LSTMs. So in LSTMs means long short-term memory, that you can have long as well as short-term memory. You can decide what to keep and what to forget. So automatically your network will learn what to keep in memory and what to forget. And a simple standard recurrent neural network, how it looks like. Just we see it here. So basically one time step, or you can say it's a one cell of RNA. And if you know our neural networks, how they operate basically using a weighted sum. They take a weighted sum of inputs with some weights, some inputs are there, and you basically sum them up along with their weights. Suppose it is W1, it is X1, it is W2, it is X2, it is W3, it is X3. So what are you doing here? You're taking weighted sum of inputs only and then applying some nonlinear function on that. Then you're getting output. This is how a neuron of the network behaves. It is just takes the weighted sum of the inputs only. So here this Rn is the same thing. That it is having, if xt is the input, so it is applying some weight to the input and having some bias also, and then applying this tan hyperbolic function. This is a single cell of RNA. And if previous A's also we are taking, then what we'll do, we will take tan hyperbolic of weights, input xt, and we will concatenate our previous hidden state. And we'll apply the bias. This is the node of a standard RNA. This is being done here. You can think this is input, this is previous state, hidden state, and you are concatenating them. And after that, you're applying weights over this network, and then you're taking a time hyperbolic function, nonlinear function. This is a simple node of a standard RNA, and these are different cells. The same thing is happening in each cell. Weighted sum and tan hyperbolic function, some nonlinear function. Since it's a hidden layer, so normally we use tan hyperbolic here. Now trend is to also to use ReLU also. And how now LCM looks different from this RNN? Now it is quite complex, you can see. Now what we are doing here in LCM that is different from RNN, standard RNN, is that we have different gates. And these gates are nothing but they are neural networks. They are very small neural networks. And these neural networks, or we are calling them gates, they will enable us to forget something, what to forget and what to remember. What should I remember and what should I forget? So when I will see that my gradient is going to vanish, I will start forgetting that part. So that will solve the problem of vanishing gradient. I can control how much I should take my gradient back. And I will just enable the forget gate, and it will not vanish. And if I have to remember some gender of the subject, then I can remember that thing. Like we have taken an example that some girl is studying in Nitter, and she or he lives in Chandigarh. You have to decide that. So using these gates, we can keep that thing in memory. And these gates will operate automatically. They will learn automatically. Different gates are there. If you know something, like if you already know ANN very well, then you must be able to understand this part. I will try a little bit. I will try to make this thing understandable to you. Is it in the next slide? So this is how it looks like. That cell state, previous cell state. So there is a concept of cell state. Every cell has got some state. So it's the previous cell state, it is a new cell state. and this is a hidden state. So first thing we have done here, we have made our hidden state and cell state different things. So hidden state is different, cell state is different. So every cell has got some state that will be decided by this network, and every cell has got this hidden state that will also be decided by this network. And then you apply some function, sigmoid like function here, and you will get your output from this cell, single cell. So just you can think we have got two things. One is cell state. What is the state of that cell? How much we have to remember that state for the next cell, that will decide. And how much previous output we have to consider to get the new output. So you can think of ST as a new output. All the output will come after applying some function here, and this is the previous output. So this network will decide how much previous output he has to take into consideration, and how much cell state he has to keep in mind for the new state. So these two things we are maintaining now. Third thing is input. This is the current input. Current input at this time step to the cell. And this different gates will, just will see it how they will work. They will help in forgetting and updating the things. So first gate is forget gate. This is a forget gate. What it is doing, it will decide what information we are going to throw away from this cell state and what information we are going to keep. So basically we will have a network here, small network here, that will give us some output between 0 and 1. And this output will be multiplied by the previous state, previous cell state. Now if output is 1, it means we are going to keep this cell state as it.
Excuse me, sir.
Yes, please.
सर ये जो कंकैटिनेशन करी है यहाँ HT-1 की और XT की,
राइट,
ये HT-1 और XT ये दोनों वेक्टर हैं. एक्चुअली वेक्टर इनपुट ही होगी, वेक्टर इनपुट दे रहे हैं हम.
हाँ जी.
जो कंकैटिनेशन से क्या मीनिंग, थोड़ी ये क्लैरिफाई कर दीजिए.
Sure. Suppose it is a vector by 100 columns, 100 rows, ऐसे 100 by 1.
जी.
Suppose our input is of 10,000 by 1. Right? So what you're doing here, you are breaking them into this form. This is HT-1 and this is XT. So it is of 100, it is of 10,000. So now we are getting Y after concatenation 10,000 100 by 1.
दोनों का नंबर ऑफ कॉलम्स, नंबर ऑफ रोज सेम रहेगा.
ये रोज है ना, ये 100 रोज 1 कॉलम.
जी.
ये 10,000 रोज 1 कॉलम. सो यू आर बेसिकली
हाँ, नेचुरली इनपुट और जो आउटपुट रहेगी वो नंबर ऑफ, थोड़ी उनपे प्रोसेसिंग होगी, नंबर ऑफ कॉलम्स, नंबर ऑफ रोज तो सेम ही रहेंगे.
तो रोज आपकी 100 प्लस 10,000 हो जाएंगी, आपकी कॉलम आपका बन जाएगा.
ठीक है सर. ओके.
एक के ऊपर रख दिया ना उसको हमने, दूसरे के ऊपर.
ठीक है सर, थैंक यू.
So this is happening here. Basically, this concatenation, why we are doing it. If you can, just I tell you why we are doing it. I will try to do it. Like suppose, basically we have two different weights. One weight is for, if I take it further, na, basically what we are doing here. One is input, na. Input is XT. So one weight is for input, that we are supposed saying it is HX. And other weight is for previous hidden layer, that is ST-1. So we are calling it a HH. So this is the thing that is happening in the network. To make it short, what we are doing, we are calculating the weights WHH as WHX together into, suppose it is WF here. And we are calculating these inputs ST and XT as I have shown here. So it's a shortcut basically. Otherwise, it's the same thing. Instead of writing this as two weights and two inputs, we are writing in a single thing, so that it becomes more concise. So what I was telling you before this question was that this gate will be the output of this gate, forget gate that we are calling. Now this forget gate will learn from this previous hidden state and current input after applying this some function here, some nonlinear function. It can be time hyperbolic or some value function, and it will generate some value, and this value will decide how much to keep the previous cell state. If it is 1, it will keep the whole cell state. If it is 0, it will forget it. It will forget the previous state. So then in that case, your output will depend only on the current input and this previous hidden state. So this is the purpose of the first gate, that is forget gate. It is deciding how much to forget and how much to keep in mind. Now second gate. So normally we call it as update gate also. So now we are having input and previous hidden state and applying some nonlinear function here and getting this input thing. We are calling it as an input gate. And it's deciding what new information we are going to store in the cell state. How much new input we are going to consider. So it is being decided by this gate. And this another gate, it's a candidate cell state. Candidate cell state. So how much new cell state we have to take it from this input and previous hidden state. We normally call it a candidate cell state. And it is again, both things are basically a small neural network. You can see it's a small neural network. You have weights here, and this is your input, concatenated input, and you're applying some nonlinear function, n plus bias. And this is also a nonlinear function. It's a small neural network. Inputs, weights, biases, and some phi function, nonlinear function. So you are going to combine these two things. So you're going to combine input, how much input you want from this new information, and how much cell state you want. And you're going to multiply them here, and then you're going to add into the previous cell state. So this output is basically how much we have to keep the previous state, previous cell state, after multiplying it with the forget gate. So it is a remainder thing. How much you want to forget and how much you want to remember. You're going to add that thing into output of this update gate. So this will give us the new information, and it is coming from old state here, and you're going to old state here, old cell state here. So you're going to add them up, right? So after this, you will have some old state and new information decided by this update gate.
Sir, I have one question here.
Yes, yes.
Sir, output of the 10H lies between -1 and 1.
Right.
जो सपोज 10H की आउटपुट है वो बिलो 0 है.
My negative है.
It is negative.
Right, right.
It means whatever the candidate cell output will be, that will be the negative.
Right, right, right.
Okay. It means that whenever we combine these two outputs of the sigmoid gate and the 10H. Here.
You mean, here only. Multiply
Here.
after here only. Here.
Whenever we multiply, before adding, whenever we multiply, we are combining the output of the sigmoid and the 10H.
Right, right.
It means the resultant of these the product, this product,
Activation.
that will be pointwise product.
We call it activation.
Haan ji, activations. It will be also negative because output of the 10H is negative.
Right, right.
Whenever this output after multiplication, we will be adding to the previous context, that is the state of the this LSTM.
cell state.
Yes, cell state.
Yes.
Suppose this output is larger than the previous context. It means
Previous
the
means
resultant of the LSTM will be negative.
you mean to say this number is small, suppose
This
0.1,
number is small,
small, and this is
and the
negative,
output number that is generated here, that is the larger but negative.
right? 0.4, like
It means the cell state will be negative.
this is not cell state. This is the new information that we have got. Like you can think in neural networks. I just tell you one normal thing.
Hmm.
In any neural network, the things can be positive, negative, both,
It
or
could be
sometimes
negative also.
some negative also. In any network, just
Yes,
we are
yes.
not
Okay, okay, okay.
any
Means
network.
negative value is also allowed. That is also the state vector.
Right. That are also allowed.
Huh.
Normally, but now trend is towards value functions. If you know this thing. Now, normally we employ them to make this function perform this value, that whatever value is coming out from previous state, either take that or make the negative value zero. Uh,
In
Normally,
practice, this LSTM is used as an alternate of the simple neurons.
negative values are fine otherwise. There is no issue in having negative values.
Okay, sir. Okay. Thank you.
There is no issue.
Okay.
Like suppose just an example, give an example why no issue. Suppose very simple example. No? Suppose you want to classify a cat or dog. So you can keep cat as a -1, dog as +1. So all negative value will move towards recognizing the cat, and all positive value will recognize the dog.
Thank you. Thank you.
Okay. So here we have just done two things. We have used the forget gate to decide what to forget and what to remember out of the previous health state. And then we have taken the new information that is coming from this ST, and ST means previous hidden state, and this new input by applying these update gates, input gate and update gates, taking their sum. So that sum of information we can decide, these gate can decide how much to keep and how much to not keep. And after then adding them up. So we have got new thing here that is containing old cell state and new information. Now we see what will happen next. Now this is the output gate. Now this output gate will decide what we are going to output finally. How it will decide? It will take the thing that we have just got that is containing cell state, previous cell state, output from previous cell state, plus new information that we got from the input. So combination of that is coming here, and you are going to decide what parts of input we are going to output and how much this input I have to directly take into account. So this will be taken from here, and it will be multiplied by the some nonlinear function. Here we are applying 10 hyperbolic function, some amount of this thing, whole thing. That we are deciding that we are having previous health state as well as some new information that we have just taken into account. So that we'll put cell state through 10 hyperbolic and multiply it by the output of the sigmoid. So we are doing here this thing. Cell state is coming from here, and you're applying this OT gate on that. OT gate means this sigmoid thing, how much to keep from this information, from new information, this network. So this is OT. This network is being shown by this diagram, this equation. And what we learned, the new city. It's a new city now. Now new city contains some information from old city plus some new information from st-1 and xt that has come through these gates. So it will have some 10 hyperbolic over this and multiply with this output. Direct output that you want direct information to be considered. So you can think of this as direct information that you want to have in your output. It is the cell state and all other things, context and all other things. So this is output. Output is our hidden state of this cell, and we can apply some sigmoid over this or some function over this and can get our output. We can predict something using this. Yes. And other thing that we are going to update is the new cell state as it. So we have two outputs of this cell. One is new cell state and other is new output or new hidden state, hidden output. And some variants of this LCM. Now this LCM basically is enabling us to forget, to decide what to forget and what to remember, and what to keep the new cell state and what to output. So it has become, it has more strength. It is more complicated. It has more things in it, so more processing it can do. And you can have some variants of this LCM, like you can have this cell state adding directly here also. Like earlier we were having these two things only. Now you can put this thing also. Some authors have tried it also. So these are called peephole connections. Taking three things instead of two things in gates. Or you can couple these two gates, input gate and this update gate. You can couple them. So different things are available, different variants. One is GRU. This GRU, it is a simpler thing, you can say it's a simpler version of LCM. And here you can see cell state and hidden state are same here. In LCM, we were having them different. We are having ST-1 here and separately cell state CT-1 here. But in this GRU, it is the same thing. They are also good. But normally, LCM, you can say, is a standard thing from where we start doing some practical implementation. But if you have some problem with your computing resources, then you can very much consider this GRU also. This is also a good thing, good performance. Now, after this theory part, we will just consider how we'll take an example of a Google stock price prediction. So we are basically taking this Google stock prices, and it's a time series thing, no? It is coming in time steps. So we'll try to predict it in a sequence. We will take like from 2012 to 2016, data we will take as input. Is it for training purpose? And for testing, then on 2017, 20 stock prices we will take of Google, and we will try to predict it after training. This is for testing purpose. So just tell you about data. It has got one date column like this. On this date, this was the opening price of the Google stock, 325.25, and how much highest it achieved on that day, how much low value it obtained on that day, and on what value it closed on that day. But we are going to just consider this column here for our implementation. So one indicator, we call it the indicator. We are taking one indicator here. Although you can take multiple indicators, like you can jointly predict open, high, low, close, all prices together. But for simplicity, we are just considering one column. So for 2012 to 16, we will take Google open price and we'll train it, and then we will test over 2017 prices, open prices. And just I show you data also. I have this data with me. This is the training data. It is in CSV format, and I have got so many rows for this. Around 12,058. So this data will be used for training, and then we will use for testing this data. I just show you this data also. So around 20 stock prices of 2017, I have this. I'm not going to use them for training. I will test my system over these prices after training. Basically, we will have some inputs of open stock prices for some days, and other days we will predict. This is how we are going to do it. This is the test data, and it belongs to 2017 years. And we are going to take this column. And just I show you Python code. I hope all of you are some conversant with Python. Otherwise, it's quite easy to implement it using libraries. So for the purpose, we are going to import some libraries. It's a NumPy library that is normally used for linear algebra things. You want to do some matrices or vectors, multiplications and all those things. You can use NumPy. Matplotlib is for the plotting thing. PyPlot we are going to import HPLT. NumPy is NP. And pandas is using bringing your data. Like your data is in CSV file, you will bring into data frame. Pandas data frame. So that's why we are importing this pandas. Now I'm using this pandas read underscore CSV function to bring this global stroke price train.csv file that I just shown you, containing 1258 records into data frame, pandas data frame. So this is data frame. This dataset underscore is a pandas data frame. And then this data frame can be sliced. Maybe we call it index location, ilog function. It's an ilog attribute basically. So what we are doing here, ilog and all rows. So this thing represents rows. Column means all rows. We are not going to select any row. We are taking all rows. And column followed by this slicing. This slicing we are doing from 1 to 2. So if you see one column in this is open. This is a one column. This zeroth column, this is one column. And we are writing up to 2. 2, this is not included. This is an excluded thing. So what we have bring in our data frame is just one column. That is a Google open stock price. So all rows of that open stock price we have brought into trading set. And values. Values means we are bringing them into NumPy values so that we can apply some NumPy function on that. Is it fine till you have any question here? It is a standard thing. And after your trading set is ready, having 1058 rows and one column, it is containing all Google stock open prices for these 4 years. Now we are going to do some scaling. We are going to normalize this data. And for that we are using sklearn. So we are bringing this min max scaler. Other option is standard scaler. So you are giving here min max scaler and feature range is 0 to 1. So which feature basically you are going to use for that purpose? And it will come in this SC variable, and then you are going to use this variable with fit transform function. Fit transform means you are going to fit means you are going to calculate also, calculate this min max scaling, and apply also. So fit means calculate, transform means apply. So basically you are going to normalize this data. Training set that is having 1058 rows of values of Google stock price, open prices of the day. And this scale data will come into, this normalized data will come into this variable. Training set underscore scale. Any doubt here? Any question here? And normally this mean max scaler, what it does, it takes every value and subtracts the minimum value of that and divide by the maximum value minus minimum value. It basically normalizes it between 0 and 1. Now next step is data preprocessing. So this is a list we are making here, X train, empty list, Y train, empty list. This is for our labels or outputs, and that is for inputs. Now since I have to predict a number here based on some other numbers, and those numbers are 1258 total, and they are in a column like this. So what I'm going to do, I'm going to take some number of days, 60 here. So I'm going to take 60 days of Google open stock prices, like on each day how much open price was. And based on that 60 days data, I'm going to predict the 61 days rate. Like how much Google stock opened on that way, had that value, open value on 61 days, based on the previous 60 open values. And to bring data into this form, we are going to apply this processing here. So we are taking this range 60. 60 is the size of data that we want in our input, and 1250 is the total number of values that we have. And in Xtrain, Xtrain is a list, empty list, and we are going to make these chunks of data, chunks of 60 values, and we want to append these values, 60 values into this list. So basically, we are making a list of 60 values, each 60 values. So first, in the loop, first thing, it will be 60 minus 60, so starting from 0 to 60. This 60 is not included, so first up to 59. So first 69 values from this 12,012 year will be the first input. You can see this up to I. I is 60, so it's 0 to 60. And 0th column is 0. So first 60 values coming into input. First list, you can say the Xtrain. You are adding it to Xtrain. Then in Y train, you are going to append the 61st value, 61 day value. Here it is 60 days value. Since we are starting from 0. The 60 day value will come into Y train, corresponding 60 day value that we want to predict. So first 60 days value has come into Xtrain list, and 61's value has come into Y train. This will happen for all records. So finally, your Xtrain will have all 60 chunks of data, 60 like one chunk, one value of 60, another value of 60, another value of 60, like that. So this will be your Xtrain. And corresponding Y train will have one value for this, one value for this, one value for this, one value. So this will be our Y train. And this will be our Xtrain. There are two lists. And you are going to bring them into NumPy array. Since NumPy array are required for us in theory. So you're converting this list to NumPy array using a NumPy array, this function, and similarly Y train to NumPy array. And you're storing finally them into Xtrain and Y train. So these are our NumPy arrays containing input and output. And next step is reshaping. Why we require reshaping? Since our model requires us data into 3D shape. Why 3D shape? One coordinate we require for batch. Like we will feed them together in batch size like 32 values together to predict. So we have a batch size of 32. So that's why we require our data in 3D shape. So what we are doing, we are just reshaping Xtrain, that is a NumPy array, that is 2D NumPy array, into 3D shape. So it is first coordinate will be Xtrain shape 0. Whatever values we have got in Xtrain, you can think how much you will get here. Almost, I think, if you take 1158 total values and you are making a chunk of 60, so you will have around 1198 values. 1198 chunks of data. The first will be this and shape 1. So shape 1 is 1 only, and you are adding 1 here. So you are having your X train into this shape 1198, 1, 1. Uh, Similarly, after reshaping, now you will import other Keras libraries. We are going to use Keras for this purpose. And in Keras is basically written on TensorFlow. TensorFlow is developed by Google. You must be knowing this thing. And to make things easy, Keras is an abstraction on TensorFlow to make things more easy for us, so that we are not need to write TensorFlow things by hand. Just we can use Keras here. And from Keras models module, we are importing this sequential model, that is sequence model. So you can add layers to this sequential model. And we are importing dense layer, means the fully connected layer. And LCM layer. So LCM is inbuilt in this Keras. Just you can use this layer, LCM layer, to implement LCM. And dropout. You must be knowing dropout. What is dropout? Dropout is a regression technique. It is basically to bring some randomness in the network, some stochasticness. So that normally we suppose we are getting some activations in layer and we drop some of them randomly. So that network is not able to like cram anything. So that's why we apply dropout. It is normally applied on the hidden layers. And this is how we will build our model. So regressor is a variable that will have the sequential model object to the sequential class. And this is a sequential model, this class is representing. And we are going to add different layers in this model. So first we will add the first LCM layer and some dropout. So to add is simple. Regressor dot add LCM that we have just imported. Units equal 50. So we are going to have 50 units. 50 in between things of the input. So if one value of Google stock is coming, we are making it into 50 values, 50 hidden values. More to get more representation out of the single value. And return sequence is true. Means we are going to return all these 50 values to the next layer. So normally it is written as true, except when you are having the last layer, so that you can have some other output we'll see it. Here we will not write this return sequence. By default is false. So all our intermediate outputs comes to the next layer. That's why we are writing return sequences. Return all 50 sequences to the next layer. And input shape we are referring here as X-tree shape. And then we are going to add dropout here. 0.2 means 20% of the activations will be dropped with probability with a probability of 0.2. So you can say activation will be dropped with probability 0.2. Then you are going to add another LCM layer with units 50, same thing, dropout 0.2. Then third LCM layer with unit 50 and with 0.2 dropout. So this number of layers, again fourth layer, we are adding. Now it is the last or less LCM layer, so we are not writing a return sequence equal to true. Since we want next output layer to have one output. And again, adding some dropout here. Now these number of layers can be any number, like we are having here 4 layers, 4 LCM layers. You can have 2, 3, 4, any number of layers. This number, how much layer you want, it depends upon. It can be decided basically depending upon experimentation. You could do a lot of experiment and see where you are not overfitting and your network is giving you good results. You can stop there. Again, this 50 number is also a hyperparameter that you can experiment with. The same thing here with dropout. You can keep any amount of dropout and you can experiment with the different values of dropout and you can see how much your network performs. And last layer is our this dense layer that will help us in predicting one number. We want to predict one number based on 16 numbers. So this is a ANN part basically, fully connected layer. Unit 1 means we want one output, final one output, one number. So that's why we are having this dense layer here with the unit 1. So this is the full model that we will use to train on the data. Any question on this architecture of the model? I hope it is clear to you. And then we are going to specify how we are going to optimize our network. Like we have different options, ADAM, RS prop, a lot of things are there. So we are going to use ADAM here. It normally uses stochastic gradient descent along with weight decaying and momentum. This is ADAM thing. And loss function that will be used to guide the training of the network is mean squared error. Mean square error. We are going to take the square of the error and going to take its mean. And after compiling and just building our network, we're going to train it. This is fit is for training. And in training, we are mentioning this is our input of 60 values, chunks of 60 values. It's a NumPy array, and it is white train is our level or output. That is one number that we are going to predict, and we are going to use 100 epochs here. One epoch takes the whole data, and this we are going to repeat for 100 times with batch size 32. 32 batch size, 32 records, 32 chunks of data will be taken together, and after that your weights are going to change. You are going to do back propagation, and then your weights will be updated. This is the meaning of batch size. And when this training of 100, it will take some time, and when this will complete, your network will be trained. And after your network is trained, just one thing remains, that you can use it for testing. And for testing, as I shown you earlier, we are going to use this data that was having 20 Google stock price open prices for 20 days of 2017 year. So this is an Excel CSV format, and we are bringing using a read underscore CSV function of pandas to data frame. And on this data frame, we are going to perform slicing to obtain all rows. Column means, and column means one column. One was open price, two is not included, and all these values into yield stock price. So our data we have obtained our data for testing purpose with these two commands. Now, how we are going to predict the data? How we are going to do the testing? One issue is there. Suppose the first, if I show you the data here, this first value, it is written in month and day. So it's a 3rd January. The 3rd January open value. Now, how can we predict it? Since we don't have previous data here. So what we'll try to do, we will try to concatenate both things, training and testing, and we'll bring these 60 values before this 3rd January into our data, so that we are able to predict this first value. So for that purpose, to bring the earlier values into our data, we are going to do this processing. So what we have done here, we have concatenated our training data as well as test data, and we are just sitting here open column. Axis 0 means vertical. Vertically, we are joining them. So we have joined our train data, that was 2012 to 16, with your test data, that is of 2017 years. So it is total data that we have, and now we are taking the whole length of that data. So that is 12. That was 1258 plus 60 minus length of test data. It is 20 and minus 60. So what impact is? You are bringing previous 60 values here into inputs. This total data, that is having 20 also. Total data is having 1258 plus 20 of test, that is 1278. So from this, you are subtracting length of test data, that is 20, and then you are subtracting 60 from it. So basically, you are keeping your input values so that you are able to predict your 60 values also. For 3rd January data, you required 60 previous values also. So bringing that thing into picture. So your inputs, you're going to reshape it into this form. So that we have done earlier also into 3D shape. And again, you are going to normalize it using the same object that we use for training. And now you are going to create this chunks of data, and you are having an empty list here, X list, and 60 is a batch size, chunk size that we require for prediction, and 20 is the total records. So we are going to take it from 60 to 80. So excess will be appended with inputs starting from 60 minus 60 from 0 up to I, that is 60. So 60 chunk of data will come into excess, and this 20 chunks will come. So first chunk having 60 values, second chunks having another 60 value. So in this way, it will go up to 80. So 20 chunks of 60 values will come into excess, and you will convert into a NumPy array, and then you will reshape into 3D shape that is required by the model. And then finally your data is ready. Now your data is ready of 20 chunks. First chunk is of 60 previous 60 values from previous 2017. Next chunk is of the 2017 first 60, like that. You have 60 chunks of 20 chunks of 60 values each. And you can give it to the model, regression model, this input, and it will give us corresponding predicted prices of 20 for each chunk. Basically, you have a chunk of 60 values, and for each chunk of 60 values, you will predict one value, like that. So these are predicted open prices, and you have to perform the inverse transformation. Since earlier you have transformed them, and you have normalized them. Now you are going to denormalize them so that they come into real picture as real data is there. So now your predicted stock price contains 20 values of predicted Google stock open prices of 2017, where each value has been predicted using 60 previous values. And now you can just plot them on the graphs. So this is how we have plotted them. Red is containing real data, real test data. It is predicted one that we have got from the model. And how real is plotted, just I show you. To plot real, plt.plot real stock prices, we already have. Just I show you from where we have got it. From there. We got the 20 values from test data set into this variable. these are those 20 values, and we are showing it in red color with label as real Google stock price. Now we have also predicted based on 60 previous chunks here. This contains the 20 values that has been predicted from the chunks of data, 60 chunks of 60 size by doing this whole thing. So this is predicted stock price, and it is in blue color, and it has a level of predicted yield stock price. So this is red, that is real prices, and it is predicted. So you can see that it has learned its trend, although it is not as close as that is not possible, but it has learned the trend. If it is going up, it is also going up. So it is doing a good job. And you are labeling X level as time and Y level as Google stock price, and it's showing later reason around that. So time and this thing has come from that thing, and these are legends. So that's all. This is how we can use recurrent neural networks for predicting time series data. Same thing we can do for text or speech or video, anything that is in a sequence that is coming with time steps, that is coming with times. So any text or any sequence or any audio thing can be converted into numbers, and those numbers can be fed into the network for training and testing. Thank you all. Any questions?